Hey scholars, we are working on right now lesson 2.6, geometric proofs. Now remember we've talked a couple different proofs. We did direct proofs, and with direct proofs we use the idea of premises and conclusions, but we still use a 2-column, and we use the stuff of law of detachment, modus tollens, law of logisms, also, or silly gizzards I like to call it, or law of contrapositives. And we were able to learn how to do proofs like in one day using that. And then our last class, we did algebraic proofs. And the cool thing about algebraic proofs is as long as you know a little bit of geometry, but mostly all of your algebraic properties, you can easily write proofs for those because you just have your statement side and your reason side of a 2-column proof, and that you are able to then get to your solution and you can easily show how it's solved. Well, now we're going to our third type of proof that you're going to be responsible for knowing, and that is geometric proofs. Now with geometric proofs, here's the hardest part. Anything you've learned in geometry is fair game. So big thing to do is go over your first chapter notes. And really any notes that we've had. Now we won't use like direct like modus tollens or law of detachment, but we actually use that kind of thought process when we're doing proofs. We will use algebraic properties in geometric proofs, the properties of congruence in geometric proofs. So there's a lot of things you have to know, but if you have not read over first chapter's notes, you're going to definitely want to. One thing is I also let you guys use a lot of abbreviations and symbols just to save space when you're doing this. So like instead of writing out the word property, you could put prop, or instead of putting write out the word angle, you can use an angle symbol, things like that will help you. The hardest thing about a proof is making sure it's so detailed. In class, I showed you guys, I asked someone to tell me how to open a door. And the idea of that, if you didn't fill in every little detail, I'd run into a desk or the wall, or I wouldn't grab the door correctly. And so the idea is a proof lets anyone who has a basic understanding of geometry basic, and then you can understand that without a doubt, your conclusion is correct. And so that's what we're going to be doing today. Now, another thing we need to go back to, remember the first day of notes. So very first day of notes. We talked about how any geometry is set up. We talked about how it starts with an undefined terms to defined terms. And then we had our postulate, which is our accepted statements of truth that are not provable. And then we get to theorems. Well, the cool thing about theorems is that they're without a fact true. So a theorem is just any statement you can prove true. So it's basically any statement that you can prove true. It's one of those, once it's proven, you can use it forever. It's one of those type of things. In fact, mathematicians are phenomenal at this. Scientists, repeat experiments over, and they say, well, now we see the phenomenon so many times it's a law. Well, in mathematicians, they prove stuff so well that there's never a chance that it could be wrong. And so it's amazing. So that's why mathematicians kind of get snobbish a little bit, because they're like, well, you have a law. Are you really sure? Is there going to be any exceptions? We know for a fact that our proof will always work. So it's kind of a funny thing between scientists and mathematicians. So we're going to go ahead and introduce you to the very first one. All right. So with this one, we're going to talk about a linear pair theorem. Now remember what a linear pair is. A linear pair, its definition says it's two adjacent angles whose non-common sides make a straight line. So this would be angle 1 and angle 2. The non-common sides would be the opposite rays, making the line that you have. So that's a linear pair. Now, what the linear pair theorem states, it states the following. If two angles form a linear pair, then they are supplementary. And remember, supplementary angles are two angles whose measures have a sum of 180. So we know if they're a linear pair. Now, anytime I see a linear pair, I can automatically assume that they're supplementary. Now, a lot of you are like, oh yeah, that's kind of common sense. Well, we're actually going to prove this theorem together, because we're going to give your introduction of a geometric proof. We're going to prove it. Now, in order to prove a theorem, you can't use the theorem in it. Remember, you're trying to show that it's always true. You are going to start, just like with our algebraic stuff, we're going to have a given, and we're going to end with our proof. And so our proof statement's always going to have our therefore symbol. And if I forget to put a therefore symbol down, please, you don't forget to put that down. Diagrams, we can also get given information from our diagrams. So we are doing what's called the two-column proof. Statements on left, reasons on right, same as we did for direct proofs, same as we did for algebraic proofs. Now, so how do we start those other proofs? We either start with a given, right? So notice our given statement is angle 1 and angle 2 form a linear pair, so that's given. Now, look at the next statement. They go angle ABC is a straight angle. Now, where in the world did I get ABC is a straight angle? Well, I got that from really the diagram. So think, here's my diagram. And the reason why I can do that, that's one thing we can assume from a diagram is a straight line. And we know a straight line makes a straight angle. So how did I know that? Because I know the definition of a straight angle. But we got it from our diagram. But if it's a straight angle, what do we know the measure of angle ABC? Well, we know it's 180 degrees because we know from here to here it's 180. And that's also the definition of a straight angle, is that it measures that. So we're going to say the measure of a straight angle is 180 degrees. So awesome with that. Now we're kind of stuck again. So we're going to use the diagram once again to help us. So look right here what our reason is. It says angle addition postulate, or other words, sum of the parts equal the whole. Well, what two angles can I add together? That's right, I can add angle 1 and angle 2 to equal 180. Oops, not 180. Measure of angle ABC. Sum of the parts equal the whole. The two smaller ones make a straight angle. Awesome. Now, remember, I'm trying to show that measure of angle 1 plus measure of angle 2 equals 180. Guys, can I substitute in 180 for ABC? Yeah, because we know they're equal. So that's my very next step. Angle 1 plus the measure of angle 2 is equal to 180, using the substitution property of equality. And if two angles measures add up to 180, we therefore know that angle 1 and angle 2 are supplementary. And so that's just the definition of supplementary angles. Now, another way you could do that would be like this. If two angles measures have a sum of 180, then they are supplementary. You could also write the definition out basically as a conditional statement, and that works really well. So, right, guys, therefore, that's our first proof. Now, here's the thing. That theorem is going to be used today. You need to know it. If it has a name, you need to memorize it. It's just that important of a thing. Now, not everything we do is still going to be proofs. Like, for instance, on this one, it says, find the value of the variables. So I'm looking at the diagram for A, and I go, and I asked you guys in class, and I go, okay, guys, how am I going to solve for this? And most people would say 6y minus 10 plus 6y plus 10 is equal to 180. And then I always ask, why? Why did I know that those two add up to 180? And again, someone will go like, oh, we just proved it in a theorem. That's the linear pair theorem. If I know two angles are a linear pair, which this angle and this one are, then we know they add up to 180. So then I get 12y is equal to 180. Y is going to end up equaling 15. Not hard, is it? Now I look at the next diagram and it looks a little more complicated. But I'm still sitting there like, I see straight lines again. Do I see linear pairs? Yeah. In fact, if you wanted to, you could do a linear pair going this way. Or you could do a linear pair going this way. And the cool thing is, you would still get the same answer. So, again, I'm going to use the idea of the linear pair theorem, or sum of the parts equal the whole, but I can choose which pair I want to do it with. I don't have to have the same one. So you might want to go 4x plus 1 plus 7x plus 3 is equal to 180, and you get 11x plus 4 is equal to 180, 11x equals 176, x is equal to 16, or 7x plus 3 plus 65 is equal to 180. I get 7x plus 68 equals 180. And 7x is equal to 112. Did I get that one right? I do believe so. Yep, 112. And then divide by 7, you're going to get what? 16. So notice either one works. You only have to ever do one. You do not have to show me overkill and give me two. Long as you're mathematically correct, I only need one way of doing this. Did everyone hear me on this? Great. All right, now we got 3 more theorems that you need to be introduced to. The first one most people think is just ridiculous to do because they all know it. It's like so amazing. I just know this, Mrs. Gregerson. Well, it's called the right angle congruence theorem, and this is all that this theorem says. All right angles are congruent. Now, when I ask you why, what's your first response? They're all 90 degrees. Exactly. And the definition of congruent angles say if angles have the same measure, then they're congruent. So really, this is almost kind of like a mini proof. We're going to talk about it right here. We're going to do a mini, like, 2-column proof. It says angle A and angle B are right angles. Great. So the next thing I would know was that the measure of angle A was equal to 90, and the measure of angle B is equal to 90. And why? That was just the definition of right angles. And then my next step is going to be substitution. I'm going to go measure of angle A is equal to measure of angle B. Now you could say, if you wanted to, transitive or substitution. I'm good with either one. So a substitution property. And then I'm like, oh look, I know they're equal in measure. So therefore I know angle A is congruent to angle B. And that would be, oops, that should be a 3 there. And that should be just the definition of congruent angles. Now, if we didn't have this phrase, all right angles are congruent, you would have to show steps 1 through 4 anytime you wanted to show a pair of right angles congruent to each other. And this is huge for later chapters, so we don't want to waste our time doing that. I'd rather just be able to look at 2 angles. I'd like to start at 1 and be able to go straight down to my last one. Does that make sense? Great. Now, again, people don't see that one's important, but know it. And I actually, even though it has a name, I memorized the phrase all right angles are congruent. It's actually easier to write, especially with abbreviations. All right, the next 2 theorems are like sister theorems. I just changed one word in there, and otherwise it's the same thing. So in the very first one, it's called the congruent supplements theorem. All right, and it says the following. If 2 angles are supplementary to the same angle or congruent angles, then the 2 angles are congruent. All right, now guys, why is this the case? I'm going to show you like the statement side of a proof. I'm not going to do the whole proof. Well, what do we know? We know angle 1, angle 2 are supplementary, angle 2 and angle 3 are supplementary. That's our given information, which then means I know the measure of angle 1 plus the measure of angle 2 is equal to 180. And I know the measure of angle 2 plus the measure of angle 3 is equal to 180 by the definition of supplementary angles. Then I can set them equal to each other. I literally can go the measure of angle 1 plus the measure of angle 2 equals the measure of angle 2 plus the measure of angle 3 by substitution property. And then remember, my goal is to show angle 1 and angle 3 are congruent because they are supplementary to the same angle. And well, I just subtract 2 from both sides. I get the measure of angle 1 is equal to the measure of angle 3. Oh look, I now know that they're congruent to each other by the definition of congruent angles. So the whole thing is the algebra and math put together, but we got it pretty easy. That's the basic idea between the congruent supplements theorem. Now, the congruent complements theorem says if 2 angles are complementary, so complementary to the same angle or congruent angles, then the 2 angles are congruent. So it's exact same reasoning behind it, except for adding up to 180. We're going to add up to what, my friends? 90. Great. Again, these aren't used often, but when they are, it's very important to know them. So I'd review your notes. Look at this top paragraph of the page. It says the following. Don't worry. I don't expect you to understand this right away. I don't expect you to be able to do proofs right away, but I do expect you to memorize theorems right away. However, I do expect you to always try. The next time we meet, we'll only be practicing writing proofs. Actually, we're going to learn some new theorems, but we will be making sure that we know these, okay? Now, I'm giving you a proof right here. And what you're asked to do is to use up here from the, like, let's just say like a word blank right here type thing. You're supposed to fill in the missing statements and reasons. That's the type of stuff I expect you to do with proofs right now. I don't expect you to be able to do a proof by yourself geometrically, but I do expect you to use your given and prove information and be able to get a good idea of the different parts. So you have to try. Don't give me any blank stuff like I just can't do it. I'm not going to give credit for that on your homework completion grade. You got to try. All right, so just like any proofs, we're going to start with our given. And we're given the fact that angle 1 and angle 2 are straight angles. So we're going to go angle 1 and angle 2 are, and we're just going to go straight angles. All right, and that's given because that was our given information. And then look at the next one. The measure of angle 1 equals 180 and the measure of angle 2 equals 180. Well, how did I know that? Well, that was just the definition of a straight angle, because the definition of a straight angle says it measures 180 degrees. Then the next step, if you notice, came from here, from 2 to 3, so I got rid of the 180. I basically used the substitution property. Now someone said, would this also count as a transitive property? And the answer is yes, it would. And after I know those two angles are equal, I know that angle 1 in measure, I know angle 1 is congruent to angle 2 by the definition of congruent angles. And don't forget your therefore sign. So that's just a simple proof when we're working with it, but you need to know those. All right, next one. It says, follow the plan to fill in the blanks in the 2-column proof. This is my diagram, so I got some lines intersecting and rays intersecting. It says angle 2 and angle 1 and angle 2 form a linear pair, angle 3 and angle 4 form a linear pair. I want to prove that if I add all 4 angles together, it equals 360. Now they gave you a plan, and it says the following: the linear pair theorem shows that angle 1 and angle 2 are supplementary, angle 3 and angle 4 are supplementary. The definition of supplementary says that they add up to 180. Use the addition property of equality to make the conclusion. All right, so first things first, how do I start a proof? Hope everyone knows you write your given statement down, right? Then it says angle 1 and angle 2 are supplementary, and angle 3 and angle 4 are supplementary. That's your linear pair theorem. And since they're supplementary, I know that they add up to 180. And that's just the definition of supplementary angles. Now notice, what was the very last step? It's the addition property of equality. What I did is I added measure of angle 3 plus measure of angle 4 on the left, and I measured, added 180 on the right to the top equation. And the reason why I can do that is because if as long as it's the same thing on both sides of an equation, I'm just using my addition property to do that. So that would be your therefore statement on this one. Not, it's easy to visualize, but it's a little bit harder to prove, isn't it? All right, last thing, we're going to try to prove. Here's the thing. Remember, if a theorem has a name, I expect you to have it memorized. Also, you want to review past notes daily to keep up to solve proofs. If you do not have your fresh knowledge in your back of your brain, proofs are next to impossible. All right, now look at the next one. It says the sum of the angle measures in a triangle is 180 degrees. So that's given to us. And we're going to prove the measure of angle 1 equals the measure of angle 3 plus the measure of angle 4. All right, so we want to show that this angle and that this one and this one, 3 and 4 add up to 1. All right, that's our goal. So first things first, you always start with your what, guys? That's right, the given. The sum of the angle measures in a triangle is 180 degrees. Now, that's what I'm going to use my very next step. I have nothing else to do, so I'm going to say that they all add up to 180. So I go to the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4 is equal to 180. And what's the reason why? The measures of the angles of a triangle add up to 180. I'm actually using the other statement, right? The sum of the angles of a triangle add up to 180. Now, it looks like we're stuck and we have nothing left to do. But remember, I got to work with angle 1 too. Well, look at this. What type of relationship do I see there? Because I can get it from a diagram. That's right, they're a linear pair. So I can go angle 1 and angle 2 are a linear pair. And that's just definition of a linear pair. And where did I get that from? Oh yeah, the diagram. Now, what do I know if I have linear pair? We know if two angles are a linear pair by the linear pair theorem, they add up to 180, right? So measure of angle 1 plus the measure of angle 2 equals 180. That's the linear pair theorem. Now, I got to somehow, notice I haven't touched number 2, combine steps 2 and step 4. But do you guys agree with me? It's actually pretty easy. I literally can substitute in this down here because it's already equal to 180 off to the right. Yeah, I know, we can actually do it. So here, my next step is going to be the following. The measure of angle 1 plus the measure of angle 2 is equal to the measure of angle 2 plus the measure of angle 3 plus the measure of angle 4. Alright, let me move that just a little bit, see if that makes sense. Okay. Now, so what's my reason for that? Oh, substitution property, because I can substitute in something of equal value. Now, I'm going to look at this, and remember, my whole goal, what I'm trying to prove, my very last statement, is to get the measure of angle 1 by itself. So we go here and just go therefore, I'm going to subtract the measure of angle 2 from both sides. So I got the measure of angle 1 is equal to the measure of angle 3 plus the measure of angle 4. And that, my friend, is just the subtraction property of equality. Take the same thing off of both sides. Now, that proof, 6-step proof, would I expect you to be able to do that by yourself? Absolutely not. But I would expect if I would not give you all the statements or reasons that you would have at least somewhat of an idea of what to put down. So no, this is hard, but make sure you get your homework done. And I'm sure you guys, you'll do great on it.